attending any conference, it's incredibly important to be there. That's kind of the only way to really dedicate your time to be there and kind of be immersed in the whole thing and not distracted by other stuff going on, even if you do get distracted with interesting conversations in the hallway.
I can't believe this. A 10x speedup with a vector? Well, that's what happened when a fellow colleague of mine replaced an unordered map with a vector. And this went against a very basic computer science fact that we all know and love, which is, for any specific operation, the time complexity of a vector, the big O time complexity, is always going to be greater than or equal to the big O time complexity of an unordered map. This is what we learn, and we are taking a temporary break. Cool. This is what we learn. This is what we use on interviews, and yet, reality differs a bit. Hi, my name is Michelle, and I'm a software engineer at Bloomberg, where I write code for the order management platform that traders use to buy and sell securities on the exchange. But I have a secret. You see, I'm actually an undercover detective because I love knowing the how and why behind the things that work. And this investigation that you're going to see hopefully encourages you to do the same. Any great detective knows that no case is ever cracked alone. So, if you have something to share, please do so at the end of the talk. But we're going to have a number of opportunities in between the talk as well for you to solve the case. And when you do so, you're going to win yourself a little detective duck. So let's get back on this case. The unordered map was replaced by a vector, and there was a 10x speedup. To really mimic what was done in production, I have my own little example over here, where what I'm doing is I have some sort of data structure, and I'm looping through this data structure. I then look for the corresponding key in an unordered map, and I get the corresponding value. And I use that value to calculate a sum. I do this for all of the keys, well, all of the values in my data structure, and the big O time complexity of this ends up being O of k, where k is the number of keys. The improvement that was done in production is something like this. Essentially, the unordered map was replaced by a vector, and once again we had the same for loop, looping through these keys. But this time, the key was an index into the vector, and we then use the value in that vector for our sum. We do this for each of the keys, and once again, we have the same big O time complexity. Except the performance and the actual time that the vector takes is 15 times faster now in this toy example that's based off of production. I tried figuring out what was going on. I asked around, and some people knew, but a lot of people did not. Code sleuths. Do you know why the vector was faster than the unordered map? If so, okay, I see a hand. Spatial locality. Why is that? Yeah. So we had a detective in the audience that said a vector essentially has contiguous memory. I'm very bad at throwing, so this is going to be fun. Good idea to just move. So there are actually a number of reasons, but the main one is a vector has contiguous memory. How many detectives in this room knew this already? Could you raise your hand? Great, a lot of detectives, and that's perfect. But don't worry if you did not, don't worry if you do. It's still going to be a super exciting investigation. We're going to first start off with caching everyone up, making sure that we're all on the same page with a few of the basics. We will then pivot onto something that I like to call cache me maybe, and this is just how to leverage your inbuilt cache. And I know this has been talked about already at this conference, but we're going to see some stuff that you've not seen before. And we're going to wrap up with cache me, maybe not. What the heck does that mean? Or rather, what the duck does that mean? Well, I'm not going to tell you because a lot of the nice detective movies and books that I've watched and read have suspense. So we're going to keep that till the very end. But trust me, it's super spicy. So the vector was faster than the unordered map because of contiguous memory. This just means that memory is ordered one after the other with nothing in between. But for the unordered map, we have our keys that are going to get hashed using a hash function into buckets. Now, these buckets actually are contiguous, but they have values, and these values are not. But why does this matter? Well, it's important because your device is going to have main memory, as well as potentially a cache or several layers of caches. If you try to access the very first element of a vector of doubles, you're going to look for it in your cache, and if you don't see it there, you're going to have a cache miss, after which you're going to go into main memory, and that little box is the first element of our vector. Woohoo! And because the vector has contiguous memory, the next few elements are actually also a part of the vector. And yes, we do only want to move that very first element of the vector to the cache, but we only move things in the form of cache lines, which are typically 64 bytes in x86, 32 bytes in ARM, but it depends on your architecture. We move this into our cache, and now if we try to access the second element of our vector, we have a cache hit. But if this was an unordered map, memory is not contiguous, and so the second element is most likely going to be on a different cache line, and we have a cache miss. So what? If there's a cache miss, who cares, right? Well, you should care because your device essentially looks something like this. It essentially has a bunch of memory stores, which are essentially caches or even primary and secondary memory. Now, the further away you are from the brain of your CPU, the control unit, the longer time it takes to actually access data. And to really visualize this, we have these little moving circles that represent data movement to and from these different data stores. The pink circle, it's super fast. It's movement to and from the register. And our two-scale diagram also has a blue circle, which is movement to and from the L2 cache. We have a green circle, which is a little slower. That's movement to and from primary memory. And please, let's not even talk about that orange circle. It's movement to and from secondary memory, and it's barely even moving. Jeez. So clearly, we don't want to have a cache miss. Now, in the world of C++, there are some data structures that don't have contiguous memory. These are just some of them. There's std_map, the infamous std_list, etc. And we also have data structures with contiguous memory. So there's the vector, array, etc. And C++26 is hopefully going to bring in std_flatMap and flatset into the standard. Third-party libraries as well already provide their own versions of flat data structures, and that's great. So let's pivot onto cache me maybe. How do you actually write code to leverage your inbuilt cache? And my detective reports tell me that maybe you've already heard whispers about these techniques at this conference. But the very first rule about being a detective is that you trust no one. So let's verify your understanding. Detectives, what if you have code like this? So you have a struct, and what you're trying to do is essentially make your struct smaller so you fit more of it into your cache and have fewer cache misses. What can you do? I see your hand. Yeah, so the comment was to put the double as the very first member variable. So I'm going to change it very slightly. I will also give you a duck. You should look at me before I... yeah, there we go. Cool, good catch. Yeah, so, or rather, good cache. No, that didn't work. What we can do is actually also swap around the ordering of the double B and character C. This makes our struct smaller. And the reason for this is essentially the order in which you declare variables in your struct is what defines the order in which they are placed in memory. So B tries to place itself right after character A, except because the alignment in this architecture for a double is 8 bytes, B is going to leave a little bit of padding after A. But if character C was right after A, the alignment of a character is just 1 byte, and so you have a smaller struct. Detectives, what about this? What if you have a struct called detective, and you have a member variable for age, number of solved cases, classification level, and a vector of these detectives? Now, what your code is doing is it's going to actually loop over these detectives and print out only the number of solved cases. And this is the bottleneck in your program, even though it does use age and classification level at other points. How do you improve this? I see a hand. Do you want to come to the mic, actually, so I don't need to repeat? Thank you.
You can use arrays of structs instead of struct.
Is that on the slide?
So
Can you?
on the slide, but also...
Yes, exactly. So this is just a recap, essentially. So this was mentioned in our keynote today by Vittorio. Great talk. All you do... Oh, duck, wait, I keep forgetting. Good, you're further away, so this time... Good catch, that was great. Well done. So what we do instead of just having a plain member variable is we have a vector of these number of solved cases. And this means when we're actually bringing this into our cache, we're going to fit more of these into the cache as opposed to when we were iterating over detectives. because in that case, we also had age and classification level in the cache. Now, I've also heard that the order in which you declare variables is super important, and it makes sense. So let's say you have an integer, you've declared x, and then you do some heavy work, where the heavy work is going to pollute your cache, and then you try to utilize x to access y. Something like this is going to be slower than if you essentially just access x right after you declare it, right? But we trust no one. That's what good detectives do. And we test this out ourselves. So I have scenario A, where I'm declaring x. I then do heavy cache work to pollute my cache, essentially trying to ensure that the next line of code is going to be a cache miss and going to give me a performance penalty. I am timing that second access. In scenario B, it's very simple, very similar. I declare x again, and I am also again timing that second access, but this time the second access is closer to the declaration of x, so I have hopefully a cache hit, and then I do heavy work at the end. And when I run this in main, scenario A and then scenario B, I see that scenario B is faster. Then I switched the order of scenario A and B. And all of a sudden, my benchmarks reversed. Literally, this is what I did in main. I swapped the order of scenario A and scenario B, and then all of a sudden, scenario B started running slower than scenario A. What was happening? Does anyone know? Hand, yes? Cache pollution, could you say more? I can't jump, I'm Thank you.
So in the first case, when you run the scenario A first, scenario A pollutes the cache, and then when scenario B gets to run, the cache is already polluted. And now he has to also flash all the writes back to DRAM and then run.
But then the second thing should be slower.
Yeah, in this case.
But the second thing is faster.
And then it means you have the opposite. They use the same data in heavy work and you already have it in cache.
That's a good guess. I don't think that was what was happening, but I will give you a duck. Thank you. And also, duck for you for passing the... So, here's what I think was happening. The very first few instructions that your program has can actually quite often run slower than the rest of your program. This is something known as, well, the reason for it is something known as clock speed ramp lag. And this is because your device is essentially trying to increase the power it receives, maintain internal voltages, and increase the frequency of your clock, just to make sure it can help you execute your program as fast as possible without violating thermal constraints and, boom, blowing up your device. What you should have done and what I should have done is used tools like CPU power to lock your CPU at max frequency before you start profiling. And in fact, tools like Google Benchmark do this for you, but I was being silly and I used Std Chrono, haha. So I just did this. I set my max frequency. Oof, still no clear winner. And this time, sometimes A was faster and sometimes B was faster. It was no longer consistent. I then realized X is actually very small. It's just an integer, right? So this means it can just live in my register, even after I pollute my cache. And so when I try to access it the second time, I'm not going to have a cache miss. That's not going to happen because I used volatile. So I was trying to use volatile just because it's a bad habit, not just of mine, but of some other people I know. And volatile essentially just tells the variable, so it tells the compiler that the variable might change, so just don't optimize this line. But this can interfere with realistic behavior. So in this case, because I used volatile, even though X was in the register, I'm kind of forced, so the compiler is forced to essentially ensure that the value of X is not read from the register, but from the cache or memory. So it interferes with realistic behavior. What you should do instead is aim to use benchmark do not optimize, part of Google benchmark, and this is more performance safe. Then I tried making X really big, so now it's a huge vector with a lot of elements. Still no clear winner. Next, I switched to using read timestamp counter, RDTSC. And this is because my measurements were just tens of nanoseconds apart. So read timestamp counter is a better tool. And then, nope, still no clear winner. What the heck? What the duck? Oh yes, we have multiple cores. So I know I showed you a diagram earlier with just a single core, but hopefully your devices have more than one core in this day and age. And when this happens, even if you have a single threaded program, you still need to make sure your program runs on only one core and that it is not interrupted mid-run. And also that nothing else actually runs on that core, thereby messing up your results. So I did a few things. I turned off simultaneous multi-threading, SMT, on my device, thereby ensuring only one task will run on each of my physical cores. This slowed down my device while this setting was on, but this is the sacrifice I make for better profiling. I then also used kernel boot parameters, and this is to ensure that the operating system doesn't run its own stuff on this core and doesn't interrupt any task running on the core that I'm trying to isolate. Finally, I used task set to pin my program to one of these cores. And my device isn't a NUMA-aware one. So if you have a NUMA-aware device, which is non-uniform memory access architecture, you use something a little different, but this also ensures your program is running on just this one core that you've isolated. Oh my gosh, still inconsistent? Are you kidding me? Nope, this is what happened. And then I took a step back and thought, is this the compiler doing some weird reordering? And I checked my assembly, and in this case, it was not. Oh my gosh, the culprit is not the compiler. It's my actual CPU hardware that's performing out-of-order execution, not at compilation time, you can't see this in assembly, but at runtime. Wait, someone said something? Prefetching? Kind of, but not exactly. Let me explain. So, out-of-order execution essentially happens when you have instructions that are independent, and you can't see it directly in assembly, but you can identify candidates. So, for example, and this is actually our example, we have heavy work that's going to be slow because it's going to be fetching things from primary memory. The CPU can decide to actually, while it's waiting for stuff to happen for heavy work, start executing instructions for using values in vector x. This means you can potentially have a cache hit even after the fact that you have heavy work right before in that code. You can turn it off, yes? Do you know how? Yeah, there's a command. That's a good point. I will give you a duck if you tell me the command. What's that? I'm working on x86. Why did you ask that? Yep. Okay, fine. True. Okay, fine. Green duck, you said. I think this is green. No, I want to throw. If you can throw the duck to him. Okay, so let me explain. I think you were probably alluding to this, but out-of-order execution kicks in, but it depends on the platform. So a lot of devices have x86 for laptops. I learned this in Bartosz's talk, by the way, which was amazing. You should watch it. And mine does too. So I have x86, and out-of-order execution happens there. But it doesn't happen in other architectures. For example, if you have, let's say, an energy-efficient ARM core, you're not going to have out-of-order execution. Boop. My slides decide to go out-of-order execution. Okay, here we go. So how do you test this out-of-order hypothesis? Yes, I know there was a mention of some special instructions, but what? What can you do to this code to test this? Anyone? For a duck? Hand? Memory barrier. Do you mean yeah, correct. So memory fences, basically. Yes, same thing. So for this purposes. Yeah, so what you can do is add a memory fence. Now, a memory fence just says any loads or stores that happen before me are guaranteed to happen before me, and any loads or stores that happen after me will happen after me. Simple enough. And then finally, we had consistent results. I was so happy when this happened. I had a mini party at home with me, myself, and my ducks. But it was great. So variable order actually does matter, but only whenever your compiler doesn't actually reorder stuff, and out-of-order execution does not happen. So most of the time, it does not actually matter. And moving declarations around can make code harder to read. So be careful of what you do, and only do it if it's a really, really bad performance bottleneck. Ooh, the time is here. Cache me, maybe not. What does this mean? For simplicity, let's just say for now, there is no out-of-order execution, and my compiler isn't going to reorder anything. You read a vector A, and then you write a lot of unrelated data to vector B, and finally you read vector A again. So that second read of vector A is going to be a cache miss, assuming that vector B, the write to vector B, polluted my cache. And that's bad. We saw that earlier. Wouldn't it be super cool if we could make sure that write of vector B doesn't go through my cache? And first rule of being a detective is trust no one. I lied to you, haha, again. And I showed you the pretty little architecture earlier, but you actually have something equivalent to a write combining buffer in all modern high-performance CPUs. It may be called something slightly different, but it exists. This write combining buffer lets you actually skip your cache. It'll send any writes to the memory controller, and the memory controller has write queues and read queues, which it will use to essentially store these writes, and eventually it'll send it to primary memory. Now, the queues that the memory controller has are used by the cache as well. The reason we're skipping the cache is because we decide to go through the write combining buffer, which is actually quite small. It's typically roughly the size of a cache line. So let's experiment. We create vector A, we read vector A. We then write unrelated data to vector B. In one test, we use our write combining buffer, and in the other, we use our cache. So that's the normal write that we've been doing this whole time. And finally, in both these tests, we read vector A. And we're timing each of these sections. And overall, timing-wise, streaming, which is what we essentially do, with the write combining buffer is faster. With SIMD instructions, it ends up being, well, roughly 63% faster. It's a little not as obvious, the performance improvement, when you have scalar streaming instructions, but it is still there. And this seems to happen whether we have out-of-order execution or not. And very interestingly, the main source of that speedup was not the fact that the last read was faster in the case of the write combining buffer, because that was my expectation, right? We're going to have a hot read now where we don't actually have in the case where we write to the cache. But that's not the cause of the main speedup. The main cause is actually that yellow write. What is happening? So I'm going to show you a little animation which represents what's happening under the hood. And in this animation, I'm using SIMD instructions, so SIMD streaming instructions specifically. But the same thing applies if you use scalar instructions if SIMD isn't available for some reason on your architecture. Yes, okay. So let's say we have our first streaming write. What's going to happen is we write 32 bytes, and it'll be sent to our write combining buffer. And we have another 32-byte write for the second streaming instruction. Now, the write combining buffer will literally combine the writes and send it to our memory controller's write queue. And at some point, the memory controller will use an I/O bus to send things to primary memory. Now, this process is going to keep happening for these writes. And once the very last write has made its way into the write combining buffer, we're going to have a read, because remember, in our code, we are trying to read vector A at the end. Except that read was going to be in cache, so it's not going to originate from primary memory, like I'm showing you here. But I'm showing you this for a reason, and I'll tell you why very soon. But let's assume now we're reading another vector, vector C. We bring this into our memory controller, the read queue, and it'll be sent to our cache, and at the same time, the memory controller will drain any writes, and the write combining buffer as well will do the same. So we're going to let this play out, and our last write reaches primary memory. Great. But what happens in the case where we write using our cache? Well, when you write with caches, there's something known as read for ownership. You need to make sure the data you're trying to write to is owned by your core. And because of that, we're going to first read the data from wherever it is, bring it into our memory controller. So that 64-byte read is going to go along that and reach our memory controller, and it will eventually be sent to our cache. But of course, if there's no space in the cache, we might need to evict stuff. So that 64-byte write is going to make its way into our memory controller's write queue. The read as well goes to the cache. And at some point, it's going to be propagated to the other levels of caches and also be written to. And at some other point in time as well, the 64-byte write will make its way back into primary memory. So the I/O bus literally flips to write mode, and we're good. I'm going to show you this one more time, but the main idea here is that this read for ownership thing isn't happening with the write combining buffer. It's only happening when you write using your caches. And of course, this whole traffic that's coming from our cache evictions as well is adding to the slowdown that happens when you write using your cache. This is why the write combining buffer is faster. We're going to do one last thing. We're going to add a read of vector B right after the write to vector B. Detectives. There's a question coming up. What if vector B was a vector of all ones before this program ran, and then you try to write 42 to literally every element that B has with your write combining buffer? When you read the value of B, does anyone know what the last element of B is going to be with the write combining buffer? Any hand? Duck. Go. Yes? 1. Why is that? Okay, I'm going to give you that. So the answer that was given was 1. You want to move your head slightly? Yeah, there we go. Nice try. So there's no fence. I think that's the point I'm giving you the duck for. So here's what actually happens. This is a quick screenshot from the animation you saw earlier. And notice how we have our 64-byte read, which originated from our primary memory. But at the same time, we have writes sitting in our write combining buffer, as well as a few writes in our write queue that the memory controller has. Detectives, what would happen if that 64-byte read was dependent on any of those writes that are sitting in the write combining buffer or the memory controller's write queue? Repeat it. Free duck. Repeat. Anyone? What happens? So the comment was the reads are deferred until all the writes are completed. This would only happen if you have a fence. But I will give you a duck. No, stay where you are. This is great. Good practice for me. See, there's a reason I became a software engineer. That is it. But, if you want to get the duck, it's now a missing duck. Now we have a case of the lost duck. But we found it. So that value that is in vector B can actually either be 1 or 42. It just depends on what made its way into primary memory. And we can fix this with a fence, like an earlier comment was made. And this will ensure that all the writes drain before the read. And actually, with this fence, our performance timings mostly get faster. And this is in the case where you don't have the read of vector B right after. If you want to know why, ask me during the Q&A or talk to me later. But basically, using a fence should be done when we use our write combining buffer. But when do you even use this write combining buffer? Well, use it when you have large data, when the data is consumed much later than it is written to. Either it's really far in your program, accounting for out-of-order execution and your compiler reordering things, Or maybe it's written, or maybe it's read by an external store later on. And of course, use this only if you actually see performance bottlenecks. Because if you have a read of that vector B right after you write with the right combining buffer, what's going to happen is you kind of lose the advantage of skipping the read for ownership phase. And so in that case, having a normal cache write ends up being better. These are just a few tools, question very soon, but these are just a few tools to profile the behavior of your cache. But in summary, you've cached it. You've understood, hopefully, contiguous memory. You've learned why avoiding cache misses is actually very beneficial. If you didn't learn it at the keynote, you learned it now. You've seen cache-friendly coding patterns, not just at this talk, but even other talks at this conference. And you've had hardware insights, which are pretty cool, I think. You've equipped yourself with the right tools. The tool you use is extremely important when benchmarking. And you've learned that you don't actually need to use the cache in certain cases. And of course, please trust other people. I know what I said earlier, but always try verifying things yourself just to build your own understanding. Here are some other great related talks. Oh, if you want to take a picture, yes, I will pause. But I hope I've cached your attention. Thank you. Any questions? I know there was someone in that corner. If you want to come to the mic here. Yeah. No, you should go walk to the mic. It's like right there. Okay. If people walk to the mic, you can ask questions. Yes. Yeah, so the comment was, I'm using a vector instead of an array. That's very true. I was using a vector here just to demonstrate things, but an array is oftentimes more performant. But yeah, good comment. Do you want another duck? And any other questions? Oh, if you want to... Okay, there we go, fix.
No, so I just wanted to ask, why is the fence actually faster, since you asked us to ask it during the...
Oh, right. So... To repeat the question, it was why was the case where you have a fence after the right combining buffer faster? I want to hit the mic. Like, I missed the mic, it's fine. But essentially, what I think is happening is when you have a fence, your memory controller actually enters into something known as write drain mode. So it's not just a normal write mode where you can actually prioritize reads. With a write drain mode, it essentially just optimizes the writes and keeps sending stuff to your memory. And that's the reason for the improvement. Great question. I wonder where you thought of asking it from. But Fedor, also, you're a great... You should watch Fedor's... He did a class. I was not there, but I've heard great things about it. So automatic duck, just because of that. But continue.
Did I understand you correctly that you were saying that non-temporal writes and the read from the same address do not respect the data dependency?
Yes, when you don't have a fence. At least this is what I saw.
So, I don't believe that is true on x86 on one core. As far as I know, reading from the same address after non-temporal writes still respects the data dependency.
Sorry. Sorry, I forgot to clarify. This is not the same address. It's a different value, right? It's the...
But it's the value you just wrote, right? So
the case where I have the read of B?
So if you write something non-temporal,
right,
and then read that address back immediately,
yeah,
as far as I know, you will see what you wrote, even if you mix non-temporal writes and regular reads.
And even if you don't have a fence?
Even without fence, yes.
Interesting. I have something that goes against that. Do you want to talk offline and I can show you?
Let's talk offline.
Yeah, but great comment. I'll give you 2 ducks if you... Wait, okay. Was it the same? Cool. Any other questions? Great. If not, thank you.